Hi everybody, in this video we are going to be solving basic trig equations. And again, this is another topic that is just going to be a challenge and we're going to work through it. You have to use some diligence, but you'll always get there if you use the right tools. So our basic strategies for solving these simpler trig equations are to use special triangles and to use our inverse trig functions. Remember sine inverse, cosine inverse, tan inverse, etc. So let's look at our very first example. In this example, I have sine of x equals 1/2, and I want to solve for x. So we've actually seen stuff like this before. I want to know what angle has sine equal to 1/2. So I might draw a triangle. And if x is one of my angles and sine is 1/2, that means that the opposite is 1 and the hypotenuse is 2. You could complete this triangle. This side would be square root 3. And then you might recognize from this that x equals, what is it? Pi over 6 in this triangle. So basically what we've said is here's our unit circle. I'm looking for an angle such that when I draw it, the y coordinate is 1/2. That means sine is 1/2. So if this is 1/2, then this theta equal pi over 6 has coordinates root 3 over 2, comma 1/2. So sine of pi over 6 is 1/2. But remember from our reference angles, there's another angle that has sine of pi over 6 equal to 1/2. That's 5 pi over 6. So now I have two possible solutions, pi over 6 and 5 pi over 6. Okay, I bet that I can find some more. Say we go all the way around the circle. So we make it 2 pi and then go pi over 6 again. Now I'm back. So I also have pi over 6 plus 2 pi. If I go another 2 pi and back, then I have my y coordinate as 1/2, so sine is 1/2 again. So also pi over 6 plus 4 pi. I could do the same by adding these 2 pi's onto the 5 pi over 6. And I could keep going like this forever by adding multiples of 2 pi onto each of these solutions, because we know that pi is 2 pi periodic. Every 2 pi it repeats, sine is 2 pi periodic. Every 2 pi it repeats the same values. So we write the general solution as x equals pi over 6 plus any multiples of 2 pi. So that's what this k represents. And 5 pi over 6 plus any multiples of 2 pi. So let me just give you another quick calculator demonstration of why this is true. So let's say we graph sine of x, and it looks something like this. Now if I want to know where sine of x equals 1/2, I want to know when this graph is hitting 1/2. So let's graph the line y equals 1/2. And I'll change my window just a little bit so we can see it better. So there's sine of x. Here's 1/2. Every time that these two graphs intersect, we're saying sine of x equals 1/2. So how many times does sine of x equal 1/2? Well, infinitely many, because this graph is going to keep crossing over 1/2. So that's what this general solution is really about. There's infinitely many solutions. And we used our special triangles to find one of them. We used the fact that sine is positive in the first two quadrants to find the second solution, 5 pi over 6, and then we just added multiples of 2 pi onto that to take into account the fact that it's periodic, that it's going to continue to reach 1/2 forever. So let's do another example here. a little more complicated. In this case, I don't have sine of x equals to something. I have 2 sine of x equals to something. So what do? I want to solve for sine of x. So I get sine of x equals 1/2. And notice that's exactly the same as our last example. So my general solution is the same. Pi over 6 plus multiples of 2 pi and 5 pi over 6 plus multiples of 2 pi. The purpose of this example was just to show you that when we're solving trig equations, usually we want to first make the equation look like a trig function, so something like sine of x equals a number, or cosine x equals a number. Because then we can use our inverse trig functions, or we can use special triangles to get the answer. So let's do a second example here. I have sine of x plus root 2 equals minus sine of x. So I want to make the equation look like sine of x equals to a number. So I'll bring the signs to one side of the equation. So if I add sine x to both sides, now I have 2 sine x plus root 2 equals 0. And I need to get a number on the other side. So now I'll end up with 2 sine x equals minus root 2. So finally, I get sine x equals minus root 2 over 2. So I'm almost done, but now I need to find x. So I'm going to use this similar strategy to before. But the tricky part is now I have minus. So I want to know, come back to our unit circle, when is sine of x going to equal minus root 2 over 2? So it's going to be this angle and this angle. So my answers are going to be in quadrants 3 and quadrants 4 because that's where sine is negative. But I can use reference angles to solve it by first solving the positive version. So first solve sine of x equals root 2 over 2. And then second, I'll move the answer into the third and fourth quadrants. So when is sine of x equal to root 2 over 2? So here's x, opposite over hypotenuse. This is our isosceles right triangle. So I have opposite is root 2, hypotenuse is 2. Since this is the isosceles right triangle, I get pi over 4 as my solution. But remember, so let's draw this again here. So there's one solution. Sine, and I need to move this now into quadrants 3 and quadrants 4. So this is my step 1. Step 2, the equivalent of pi over 4 in quadrant 3 is pi plus pi over 4. So that's 5 pi over 4. And in quadrant 4, it's almost 2 pi, but it's pi over 4 short, so it's 7 pi over 4. Now to get my general solution, I just add on multiples of 2 pi. Because it will keep repeating as I make full circles and get back to these spots, 5 pi over 4 and 7 pi over 4. Okay, so one last example for these basic ones. Let's say I have 2 sine x equals minus 0.5. I need to get it to look like sine x equals a number. So I'll divide both sides by 2. So now I get negative 0.25 because if I do negative 0.5 divided by 2, I get negative 0.25. Now, there's no special triangle that's going to allow me to solve this. So what I do is I'll take sine inverse of both sides. Because sine inverse of sine of x will just leave me with x. And on the other side, if I do sine inverse, so notice right here above sine in blue it says sine inverse. So I click second, sine inverse, negative 0.25, enter, and I'll get this answer, negative 0.25268 approximately. So this is the angle in the fourth quadrant, which solves my triangle. So in order to get more solutions, I would look at this angle in quadrant 3. So this is the quadrant 4 solution. The quadrant 3 solution is going to be pi plus this angle. So I do pi plus my recent solution. So that gives me 2.889. And now to get the general, I take these two solutions and I add multiples of 2 pi. So 2.889 plus 2 pi k gives me all these quadrant 3 solutions, and negative 0.25268 plus 2 pi k gives me all the quadrant 4 solutions. So we'll keep playing with this. I know that the general solution might be a little tricky right now, but the idea is just that your values of sine and cosine continue to repeat as you go on forever because these functions are periodic. And so we'll get used to using that notation. And sometimes I'll just ask you for a solution between 0 and 2 pi. And in that case, you don't have to worry about the general solution. We'll do some examples of that in the next video. So I'll see you again soon.